I want to differentiate tangent theta. How am I going to do this? Well, you hopefully remember that tangent theta is sine theta over cosine theta. Why is this? Well, if you think back to the business about the right triangles, right? Sine is this opposite side that I'm calling y over the hypotenuse, and cosine is this adjacent side whose length I'll call x over the hypotenuse. I'll call this angle theta. Then sine theta is y over r, and cosine theta is x over r, so this fraction can be simplified to y over x. That's the opposite side over the adjacent side. That's tangent of theta. So good. I can express tangent theta as sine theta over cosine theta. How does that help? Well, I know how to differentiate sine and cosine, and by writing tangent this way, tangent's now a quotient, so I can use the quotient rule. All right, so I'll use the quotient rule, and the derivative of tangent theta is the derivative of the numerator, which is cosine, times the denominator, which is just cosine, minus the derivative of the denominator, which is minus sine, times the numerator, which is sine. And this whole thing is over the denominator squared, cosine squared theta. Now, is this very helpful? Well, I've got cosine times cosine, so I can write that as cosine squared theta. And here I've got minus negative sine theta times sine theta, so that ends up being plus sine squared theta, and the whole thing is still being divided by cosine squared theta. Can I simplify that at all? Well, cosine squared plus sine squared, that's the Pythagorean identity. That's just 1. So I can replace the numerator with just 1, still over cosine squared theta. And 1 over cosine squared theta, well, 1 over cosine is called secant. So this is really secant squared theta. So what all this shows is that the derivative of tangent theta is secant squared theta. A moment ago, we did a calculation using the quotient rule to see that the derivative of tangent theta is secant squared theta. And now I want to see how this plays out in some concrete example to get a real sense as to why a formula like this is true. So here's a couple triangles. They're both right triangles, and the length of their hypotenuse is the same. This angle I'm calling alpha, looks to be a little bit less than 45 degrees. And this angle I'm calling beta, and it's more than 45 degrees. Now what can you say about the secant of alpha and the secant of beta? Now, the secant of alpha is definitely bigger than 1. I mean, what's the secant? It's this hypotenuse length divided by this length here. And that's bigger than 1. How does it compare to beta? Well, the secant of beta is quite a bit bigger than the secant of alpha. And why is that? Well, the secant of beta is this length here, the hypotenuse, divided by this width. But this triangle is quite a bit narrower than this triangle. So the secant has the same numerator, the hypotenuse, the same length, but the denominator here is quite a bit smaller. And if the denominator is a lot smaller, then the ratio, which is the secant, is quite a bit bigger. So I know the secant of beta is bigger than the secant of alpha, and the secant of alpha is bigger than 1. And that means that secant squared alpha is also bigger than 1, and secant squared alpha is less than secant squared beta. And the significance of that is right here. The derivative of tangent theta is secant squared theta. So what does this mean? Well, this is telling me how wiggling theta affects tangent. It affects it like a factor of secant squared theta. So in this example, where secant squared beta is a lot bigger than secant squared alpha, the effect of wiggling beta on the tangent of beta should be a lot larger than the effect of wiggling alpha on the tangent of alpha. And you can see that. Let me draw a triangle where I've wiggled the angle alpha up a little bit. I've made it a little bit bigger. All right, but I'm going to make the same hypotenuse. All right, so this hypotenuse length is the same as this length, but I've made the angle a little bit bigger. And how is the tangent of the slightly larger alpha compared to the tangent of alpha? Well, the tangent of the slightly larger alpha is bigger than tangent alpha, but not by all that much. Now compare that to when I wiggle beta up by the same amount. Right? I make beta a little bit bigger right? So I make beta a little bit bigger by the same amount that I made alpha larger, and then I think about how that affects the tangent of beta. Well, the tangent of beta is this height divided by this width. And you can think about it. I mean, this height maybe isn't increasing a whole lot, but the width of this triangle is getting quite a bit narrower. And because it's the ratio of that height to that width, the tangent of the perturbed value of beta is quite a bit larger than the tangent of beta. And you can, it's reflected in the fact that the secant squared beta is a lot larger than secant squared alpha. So these kinds of facts, right? The fact that the derivative of tangent is secant squared theta, you can really get a sense for why these things might be true by thinking about triangles and how wiggling the angle will affect certain ratios of sides of the triangles. But if this seems a little bit too abstract, we can kind of pull back a little bit and do a numeric example next. And maybe the numerical example is sort of another way to see a formula like this in action. Let's do a numerical example to get a sense as to what you might do with the fact that the derivative of tangent is secant squared. Here's an example. Let's try to approximate the value of tangent of 46 degrees. Why is this an interesting example? Well, we know the tangent of 45 degrees exactly. I can figure that out by looking at a triangle. Here's the angle 45 degrees, the right triangle. Because the angles add up to 180 degrees, this is 45 plus 90 plus what? Well, this must also be 45. This is an isosceles triangle now, so these two sides are the same. The tangent is the ratio of this side to this side. Because they are equal, that ratio is 1. So I know the tangent of 45 exactly. It's 1. But I'm trying to figure out an approximation for the tangent of 46 degrees. The derivative tells me how wiggling the input affects the output. So I can use this fact and the fact that I know the derivative to try to approximate the tangent of 46. And in particular, the tangent of 46 degrees is the tangent of 45 plus 1 degree. Now here you can see how I'm perturbing the input a bit. And this is exactly what the derivative would tell me something about. And a little bit of bad news, the derivative of tangent is only secant squared if I do the measurement in radians. So let me convert this to a problem in radians. In radians, it says the tangent of pi over 4, which is 45 degrees, plus what's 1 degree in radians? It's pi over 180 radians. Right? This is what I want to compute. I'm going to compute the tangent of pi over 4 plus pi over 180. And I'll do that with this approximation using the derivative. So according to the derivative, this is about the tangent of pi over 4, which is the tangent of 45 degrees, it's 1, plus the derivative at pi over 4, which is secant squared pi over 4, times how much I wiggle the input by, which is pi over 180. Now I know the tangent of pi over 4, it's 1. What's the secant of pi over 4 squared? Well, if I pretend that these sides have length 1, by the Pythagorean theorem, this side must have length square root of 2. The secant is hypotenuse over this width. So the secant of pi over 4 is square root of 2. So secant squared pi over 4 is square root of 2 squared, which is 2, times pi over 180. Now, if you know an approximation for pi, you can compute 2 times pi over 180 plus 1, and this is approximately 1.0349, and it keeps going. I mean, pi is irrational. And this is not so far off of the actual value. If we actually compute tangent of 46, the actual value is about 1.0355, and it keeps going. And 1.0355 is awfully close to 1.0349. So we were successful to use the derivative to approximate the value of tangent 46 degrees.